Good morning. Good morning, chemistry class. I hope you guys understood the last lesson pretty good. I hope you're doing okay with your work. And yeah, Lonnie, that table you sent me with different masses of protons and neutrons and electrons and the different people that discovered, Thomson, Chadwick, and Rutherford. That was a great table. That's really cool you have that. It's good to see that you have covered this stuff and that this is kind of a refresher. So when we get to the harder stuff, you'll know what's going on. Okay, so hopefully you guys answered the questions because today I'm going to go over them right now. All right, so 20 and 21, whoever wrote these, they're kind of funny. But so 20 was explain how the type of an atom is defined. Okay, and 21 was which subatomic particle identifies an atom as that of a particular element. So I mean the answer is kind of the same for both, sort of. Right? So we'll do 21 first, right? Which subatomic particle identifies an atom as that of a particular element, right? So we have our options, neutrons, protons, or electrons. Remember, protons are what defines an atom as that of a particular element. Like if it has one proton, that's hydrogen, 2 protons, that's helium, 12 protons, that's carbon, I think. Hopefully you guys have your periodic table too, because that way you don't say dumb things like I am without my periodic table, because it's on the computer, but I'm using the computer to film. But you need your periodic table, okay? But the way it works, it's of the same element based off of protons. So they can have different numbers of neutrons, but it's the same element if it has so and so many numbers of protons, okay? So the protons are what defines an atom as that of a particular element. So let's come back to number 20 then. Okay, explain how the type of an atom is defined. This is weird wording, but basically, protons determine which element the atom is, while neutrons determine which isotope of each element the atom is. Remember, an isotope has the same number of protons but different numbers of neutrons. Okay, so in order to the type of an atom is defined. So different isotopes are defined by their different numbers of neutrons. Different numbers of neutral particles. But the type of element that atom is defined by the number of protons that it has, okay? So as long as it has, 2 protons, that's going to be helium, okay? But it has different numbers of neutrons, it's still helium. It's just different isotopes of helium. So the isotopes have a definition of having different numbers of neutrons. But the same number of protons it determines what element the atom is, okay? Hopefully that makes sense. If it doesn't, let me know, okay? So then we have 22. Explain how the existence of isotopes is related to the fact that atomic masses are not whole numbers. Okay. So, the existence of isotopes is related to the fact that atomic masses are not whole numbers. It's because if you have different isotopes, here we have an example. We have chlorine, okay? So there's 2 different isotopes of chlorine, according to this EDU system told me this, okay? But so 76% of all chlorine is chlorine 35, which means that its atomic mass is close to 35. It's not exactly. We'll calculate those in a sec, okay? But then 24% of chlorine is chlorine 37. Okay, which means its atomic mass is closer to 37. So when you average the two, it's an average of the two. So you'd say, so 76% of all chlorine weighs 35 atomic mass units. And 24% of all chlorine weighs 37 atomic mass units. And so if you multiply 0.76 times 35 and 0.24 times 37, you would get 35.433. See? So it's closer to 35 because 76% of all isotopes of chlorine are chlorine 35. So it's closer to 35, but it's not 35 exactly. It's 35.43. It's almost 35.5 because 24% of the chlorine isotopes are chlorine 37, and those pull the average up from 35, closer to chlorine 37. Okay? So basically, that's a weighted average. So you say, it's like in the grade book or something. If a test is a higher percentage of your grade, then it's weighted higher, right? So atomic masses are weighted averages of all the different isotopes. That's why it's closer to 35 than it is to 37, because 76% is chlorine 35 and only 24% is chlorine 37. Okay? And then all isotopes contribute to the overall atomic mass of each element. So basically, like if there's 4 isotopes or 3 isotopes, no matter what percentage, you could have 0.01% of isotopes are chlorine, or different, whatever, chlorine 36 or something, right? But they still contribute to the mass, okay? So every time, that's why it's not a whole number. So it's not a whole number because it's an average of lots of different isotopes. Well, not lots, like 3 or 4 usually. 2, 3, 4. Different isotopes. It's an average of the different isotopes, and averages aren't whole numbers because it's an average, you know. If you say, oh, well, I got 100% on my first test and I got a 90% on the second test, what's the average? It's 95, right? So that's how averages work. Now we'll work on calculating. These next 2 are for calculating. Hopefully this won't be confusing. Okay. So 24. These are just right out of your Eddie system, okay? So calculate. Copper has 2 isotopes, right? You have copper 63. I feel like this is okay. Here we go. Copper 63 with an abundance of 69.2% and a mass of 62.930 atomic mass units, okay? And then you have copper 65 with an abundance of 30.8%, right? And the mass is 64.928 atomic mass units, okay? Now remember, based off the lesson last time, the way we do this, the total mass contribution for each isotope, you take the percent abundance multiplied by the mass, okay? Mass times percent abundance. So, for copper 63, 62, we take 62.930 times 0.692. Okay, what do you get? So you want to keep the numbers in your calculator, and then we're going to add them together because we're trying to do significant figures, which you guys learned about. So I'm going to write it here, and I'm going to write. You don't round until you're done. Okay, so I'm going to write 43.54756. Okay, you want to keep at your accuracy, and then for 65, copper 65. You have the mass is 64.928 times 30, right? So you guys know about percents. To make it, you move it over twice when you're multiplying because it's a percentage. It's a part of 100. So you go times 0.308, okay? And you guys should get, hopefully you're doing this with me or you did it already. You should get 19.997824. Okay? Now if we add those 2 together, plus, summa, you get 63, okay? 63, so I'm standing right in the way. 0.54534, right? But that's not how you do it, because you see how many significant figures we have? These both come out to 3 decimal places. So you want your answer to be out to 3 decimal places. So you just round. So it's 63 point, man, you can't see me. 63.545 AMUs. And that is the way, and you can check. If you look at your periodic table right now, I wrote it up here. The atomic mass of copper is 63.546. What did we get? 63.545. That's pretty darn close. That's how we know we did this problem right. Okay? You know you did it right if the number you get is the same number on the periodic table. Okay? So, and that's why you round. So the reason it's different by 0.01 is just because of rounding. Like we don't have, the numbers they gave us weren't exactly specific. And so when as a result, our number isn't perfect. But the key is you don't do this rounding to 3 decimal places, right? You don't do this until you're done. So see how I have lots of digits up here? I just took the numbers in my calculator and added them together. And then you round at the end. Because if you round each step, you lose accuracy, okay? Hopefully I'm not losing you. I think you guys should have learned some about significant digits, but that was supposed to be a little review, okay? So you can check your answer with the periodic table. You'll see copper is 63.546. So we're really very close. We did a good job. Now this next one's even harder because there's 3. So you have magnesium. It's the same thing, exactly the same thing, except it's with magnesium, and there's 3 of them. So you have magnesium 24, magnesium 25, magnesium 26. I didn't write the mass contribution, mass times abundance this time because I'm running out of space on the board, okay? But you guys should know. So for magnesium 24, we have 78.99%, right? So when you're calculating, that's 0.7899 times 23.984 AMUs, right, which they gave us. That's the weight, because it's magnesium 24. It's close to 24, but it's not exactly 23.985, okay? That's 18. It's hard to write sitting down. 18.9457515. Okay, great. So remember, you can just keep this in your calculator. You don't have to, you can write them down. It's good to show your work, okay? But you can, when you add them, you don't have to type them in. You can keep them in your calculator and do it again. So then this time is 10%, right? So 10% is 0.1000, but you don't have to add those, times 24.986, okay? That gives us 2.4986, okay? And then the last one is the magnesium 26 at 11%, 11.01%. So you go 0.1101 times 25.982. And that gives you 2.8606182. Okay? So now we're going to add those up, remember? So there's the same as the last problem. We just have 3 isotopes instead of 2. Okay? So let's add them up. So you have 2.86 plus 2.49 plus 18.94. What does that give us? That gives us 24 point, hopefully you guys know what that gives us because you've done this problem already. 24.3049697. Okay, but remember, 3 sig figs. Alright? In this case, they did the actual decimal, the percentage is different. But we'll do it, you have to do it to the least number. So it's point to 3 decimal places, okay? So if we look at this, right, 24.3049, we want to keep it to the 4, right? But since it's a 9 here, we round up. So then you get 24.305 AMUs. And I am done with the problem, okay? So you can check, right? I wrote it up at the board. The magnesium, you look at your periodic table, the atomic mass of magnesium is 24.305 AMUs. And we got exactly 24.305 AMUs, okay? So that's how we know we got the right answer. You can check, okay? You check your answer with the periodic table in these instances. So hopefully that makes sense, and hopefully you see now how when you have different isotopes with different abundances, right, different percentages, that's how you calculate what the atomic mass is, okay? Now, Leilani, I think Leilani, hopefully you got this pretty good. Leilani, you probably got it too, but I know you don't like math. So hopefully these problems are both the same, and there's more if you want to do them in any system to practice. Okay, but this is important because this is when you look at the periodic table and you see the atomic mass on there, and you see, oh, magnesium weighs 24.305 atomic mass units. How did they get that number? Now you know how they got that number. They took the average of the 3 different isotopes. Okay? All right. Hope this video was helpful. I'll see you later this week for our next lesson. But until then, hopefully you review this, and hopefully you guys are doing great. Keep working hard. See ya.